All right, welcome to an introduction to alternating current or AC electricity. This is an extension and application of induction. It's particular to the IB program, but it's worth knowing both at the IB and AP level. So what we really want to do in this is understand how voltage, current, and power changes with time when you have a generator that's creating electricity that's alternating its direction and therefore its magnitude with time in a nonlinear fashion. We're going to derive an equation, kind of with some calculus, but we're going to keep that to a minimum. And what we want to recognize is A, what the graphs look like, conceptualize how voltage and power change with time, and then eventually come up with a way of quantifying average voltage or power for an AC, because it's slightly different than how you do it for direct current, which we learned last year. So let's start with Faraday's law, right? Basically saying the EMF of something is equal to negative times the number of coils and the rate of change of flux. Okay, so in a generator, we need to change flux, but a generator is basically a bunch of coils of wire, right, surrounded by a magnet of some sort. I'm just drawing a very crude picture. Don't draw that there. But the point is, if flux is B times A cosine theta, right? We know that. That's what I'm talking about right here. The magnet is set in the generator. You're not going to be changing that. It's basically fixed in place. The area of the coils is not going to change. They're just sitting there. So the only way you can change the flux is not by changing B or A, but by changing the angle. And how do you change the angle of the A relative to the B? Well, you spin it around. That's the easiest way of doing it. Okay, so what I've just explained there is all encapsulated in this box. So there are three ways you can increase the induced EMF. We're going to come back to that in a few minutes. Let's derive an equation for how we would calculate the EMF as a function of time. So first we're going to do is look at this as a few key points, okay? So we have a loop of wire as represented by here, and the red represents a B field that's passing through it. So at this time zero, the way it's oriented, if I draw a normal to the face of that loop, okay, it's coming perpendicular to that loop, I see the angle between the B field and that normal is 0 degrees. So at the first instant we have 0 degrees and the cosine of 0 is 1. So our flux at that moment is at a maximum. So with the product of B and A. A bit later the angle is going to change because we're spinning it. So let's pretend we have oriented so that's 45 degrees. So in other words, the loop is, if you will, oriented like that such that this angle is 45 degrees. Well, cosine of 45 is radical 2 over 2, B times A, so it's a fraction of the BA. And then if we rotate it a little time later, such that the loop is oriented 90 degrees, essentially like, here is the loop, so I'm going to try to draw this. That's probably a mistake. Right, here is the loop, and here are the waves coming out. Then we see that the face, the normal to the face is like that, and the angle here is 90 degrees, so the cosine of 90 is 0, and we have no flux. Okay, so we've gone from a maximum to 0 in a quarter of a turn, and if we turn it the next quarter, we find now that it becomes negative. All right, and this is something we could explain in the last chapter with Lenz's law. When you change direction of the loops, if this was originally positive, negative, when you flip it, okay, at a half a turn or a quarter of a turn, then this becomes positive and negative, okay, and then it keeps fluctuating like that. So we can look at how flux changes with time. So based on here, at time 0, it's B times A. At a little time later, it's a little less than that, but not quite half, and then it's 0, and then it becomes negative, and it increases in a similar fashion until it reaches a peak in the opposite direction. And then we can imagine as we complete the turns, it follows this pattern a little bit more, and you see we get a familiar curve. In other words, we see that flux changes with time as BA times the cosine of theta. Okay? Now, if we want to calculate the EMF is by definition the negative rate of change of flux, then we can deduce that the EMF is nothing more than a negative of the slope of that curve. Now, if you do a little bit of calculus, you will find that the EMF is going to be proportional not to the cosine, but the sine. In other words, sine is the slope of a cosine curve. Long story short, it's actually negative sine is the slope of a cosine. Or from calculus, if I want to take the derivative of cosine, let's say of x or a times theta, right, then that's going to be equal, the derivative of that is negative a sine of a theta. And since we want to do the negative of the slope, we're going to end up with a positive sine value. And theta, in this case, is like an angular displacement. That's going to be equivalent to omega times t. Okay, so we learned that last year, where omega is the angular velocity, how many radians per second that thing is rotating around. And then we can also relate omega to frequency. So that's also equal to pi f. You've probably forgotten that, but that's a useful relationship. So if we put it all together, here's what we get. If I want to take this equation and find the slope of it, or take the derivative of that, what I'll end up with is EMF, because that's Faraday's law, and I'll end up with N, that's the number of coils, times BA, that's from up there. Okay, there's going to be an omega in there, because when I take the derivative of this part, remember that's omega t, I'm going to have a derivative, the omega up front, and then the sine of omega t. Okay, the negatives went away because the derivative of cosine is negative sine, and remember by Faraday's law it's a negative of the slope. So the negative times negative gives the positive. So there's a nice looking equation. So if I want to plot that over here, I see at time 0 the sine of 0 is 0, so we're going to have no EMF. So when we have a maximum flux, we have no EMF because no change going on at that instant. And then we are going to reach a maximum, and that maximum, epsilon naught, is equal to nothing more than NBA times omega, WMBA, and then it's going to drop to 0, go to a negative max, and then rise, and we get our familiar sine curve. Okay, so this is flux, this is EMF. This is the slope of that, I should say the negative slope. So we go from a positive cosine to a positive sine. Now, an interesting question that's not on here. What if we had twice the omega? What would happen to our EMF? Okay, so if you look carefully at this equation right there, you'll notice that omega appears twice. Once out front and once as part of the sine. So let's take each one in turn. If omega is out front, that means we're going to get double the EMF. And if we put the twice in here, we're going to get twice the frequency. So if I were to draw this again, I would have to draw, and this is going to be a little bit tough, I would draw big amplitude and twice the frequency. Whoops. Okay, this should be just as high. So that's an IB question you want to know, is how would things change? I think most people understand if we double the double the angular velocity, we would get a shorter wavelength or a higher frequency, but we might forget that the amplitude would go up, we get greater EMF. So that brings us back to here. What are the ways we can induce that? If we look at the NBA omega sine omega t, then it's pretty clear we increase the number of coils. We increase the flux change, okay? All right? So and then we decrease the time over which the flux changes. In other words, that just means increase omega. If you increase omega, you're basically taking care of both of these at the same time. All right. So let's look at now how we measure this output and what we rate it for. If I have an outlet that's AC, okay, it's a little bit more complicated than one might expect. So this is just a crude vision of a generator, okay, where we have a loop of wire that's rotating within the presence of a magnetic field, and we get an output voltage. And if we plot that output voltage as a function of time, we get this nice little sine curve that we just talked about. So notice the max values. They're 170 and a negative 170. So we're going to now relate this to what is done in standard industrial applications, okay? So we should know by now that in America and Canada, not Europe, that we market our voltage as 120 volts AC. But if you were to put a voltmeter into the socket and you were able to measure it every, tenth of a second, you would find that it actually varies between 170 and negative 170 volts. And that's odd, all right? And that's what this graph is reflecting up here. Why would we say that that outlet is 120 volts if it's fluctuating between 170 and negative 170? So what those ranges represent is sort of an average. Okay? All right, let me put it another way. The 120 volts represents a sort of an average between these two. Now you should reflect on that, because when I say that, you might think that the average between this and this is nothing more than 0. Okay? So how do we get an average value when we're fluctuating between two extremes that where one is positive and one is negative and not get a 0 value? In other words, where does that 120 come from? So we're going to introduce to you an interesting concept called the root mean square. So long story short, or spoiler alert, but we're going to expand this out. The 120 volts that we rate our outlets, or the 220 we rate in Europe, is the root mean square of the extremes when we have a generator moving with a certain angular speed and a certain number of coils of wire, etc. Okay, so how do we find the root mean square of this particular sine curve? And if you don't follow all this, that's not a big deal. What matters is you'll be able to apply the end result of that. Okay, so let me try to do this to make sense, because it's worth trying to understand. In the first graph below here, we have a replication of that sine curve. So in order to get an average that doesn't come out to be 0, what we're going to do is we're going to square this curve. Remember, so right now, this is a sine curve. Sine of omega t, or just a sine. So if we square it, it's going to look like this curve. And what essentially happens, I know that didn't show up very well because everything is red, is the negative parts, the troughs of this one, simply flip up to right here. So where it once before was like this, we've brought it positive, and because we squared it, the amplitude is going to grow as well. So going from this, if this is sine, this is essentially sine squared of something. And so everything is positive. And so it's not hard to take a positive value of something. Now, how do we get the root mean square? Since we squared it, we're eventually going to have to square root it again in order to get back to an EMF rather than an EMF squared. So in essence, what's plotted on this axis is not epsilon, but epsilon squared, whereas this was just epsilon. All right. So this is the tricky little thing about this, and I'm going to try to make this clear, and hopefully you'll see what I'm talking about. If I look at this first part right there, okay, what I can notice, let me erase that, is that here is the crest from the first graph, and here is the trough from the second graph, or from the first graph as well. So we understood that the average for the first graph between the positive and negative was 0. In other words, it was right along here. The average is this line there. So it makes sense that the average of this squared one is along this line here. So that's why you have a dotted line there. Or it should be a dotted line. It might not look like that on your paper. So that represents the average value of that, and if the bottom is 0 and the top is the epsilon naught squared, then it would make sense that that middle line is epsilon squared over 2, 1/2 of that. So now we can do our root mean square. So all we're doing by squaring the function, we've moved the bar, the average, from a 0 position to a epsilon squared over u. So what we can say is root mean squared, this, right, that's the y-axis, is going to equal the average, is going to be equal to epsilon over 2 quantity squared. Okay, so now if I want this in terms of the square root of this, I take the square root of this side and take the square root of this side. I'll call this E RMS, root mean square, equals the square root of this term, which reduces to epsilon naught all over radical 2. Okay? Where this is the peak. So if I want to, let's think about this. In the numbers we have there, this is 120. This is what we rate US outlets. we saw from the graph that that's 170. And if we look at 170 divided by